Hi, chemistry students. Let's talk about thermodynamics and its connection to equilibrium. Essentially, we'll be talking and creating an idea of how standard and non-standard conditions are related to the equilibrium ideas that we've possibly seen earlier. All right, so first off, what do we mean by standard conditions? Well, just remember that standard conditions are when we have every gas at partial pressure of 1 atmosphere and every solution, every solute would have a concentration of 1 molar. So this is a very specific set of conditions that we're going to start our process at. We control this and we set it up. Whenever we have that, we give it this little naught. All right. So what we know is we've seen these tables of Gibbs free energies of formation, the standard Gibbs free energies of formations, in the back of the book. And we can use those with Hess's law calculations to find the actual Gibbs free energy, the standard Gibbs free energy of a reaction. Well, what does that tell us when we get that value? Well, if delta G naught is less than 0, then if we start under standard conditions, we'll move as written spontaneously from left to right. However, if it's the other way around, if the standard Gibbs free energy is greater than 0, then our process will not move spontaneously as written. If it does move, it will move from right to left in the opposite direction as written. And the question is, where does it move to? Well, it moves to equilibrium, because that's where all processes move if they're not at equilibrium. I want to make a note right now that when you're talking about standard, you have to write this little naught, because there's a huge difference we're going to see between what they tell us. This thing right here, this naught, tells us that this number is based on these standard conditions, and it's going to later relate to something else that's very important. All right. Well, what about non-standard conditions? What if we're not sitting there at 1 atmosphere and 1 molar for all these things? Well, since we can already compute this value right here, the standard Gibbs free energy change for the reaction, wouldn't it be nice if we could use that as a starting place and then just have an adjustment factor that worked and gave us our delta G for the reaction? So this is our regular delta G, just our non-standard delta G. And it turns out there is a relationship just like that. It's developed in a physical chemistry course, so the derivation of it's not applicable now, but just trust that this equation is true. So under constant temperature and pressure conditions, we would find that the Gibbs free energy for the reaction is equal to the standard Gibbs free energy of the reaction plus this RT natural log of Q. So this right here, the delta G, represents the Gibbs free energy change for any conditions, whatever conditions we're at. This, of course, is our standard conditions. That's what the naught's all about. And then finally, we have the reaction quotient in here. The reaction quotient, if you think about it, it is actually an expression of what our conditions are now, because it's the Q that we've seen before from equilibrium. It's the relationship between the products divided by the reactants, all raised to their stoichiometric coefficients. So it's telling the story of how is the reaction. What are the conditions now? They're not standard. What are those conditions? So, by the way, remember that we get delta G naught from the balanced reaction and tabulated data, and we get our reaction quotient from the balanced reaction and our initial conditions. And we'll see an example of that later. All right, so what do we do here? Let's say we're looking at our relationship that we just created, and we think, what's it going to be like if we actually reach equilibrium? When we reach equilibrium, what's going on? So here's our relationship, and there are some things we're supposed to know about equilibrium, some definitions of equilibrium. So at equilibrium, one thing I know is that the regular old Gibbs free energy change is 0. I also know that Q is equal to K when I reach equilibrium. Therefore, if I substitute those in, I get a simpler expression, and I can rearrange that, and most people know this as a relationship between the standard Gibbs free energy and the equilibrium constant right here. The important thing is, this tells us that the standard Gibbs free energy is another way of talking about the equilibrium constant. Okay, so if K is very, very large, okay, if K is greater than 1, then the natural log of K is positive, and that means that the delta G naught will be negative. Take a look at that. If K is greater than 1, then the natural log of K is positive, and this negative sign here we'll make this entire right-hand side negative. That means the delta G naught will have to be negative. Vice versa, if k is less than 1, between 0 and 1, the natural log of k is negative, and the negative times the negative is positive, and our delta G naught will be positive. So we know a little bit about how our equilibrium lies just by the value of delta G naught. Think about it. Large K means we favor products. A delta G naught that's negative then means we favor products, and so forth. We'll summarize this a little bit later. One last thought. You must be able to derive this equation yourself down here at the bottom. This will not be given to you on any exams. Okay, so let's summarize this right now. The Gibbs free energy itself, this change that we get, it tells us about whether something is spontaneous or not. If it's less than 0, we're spontaneous as written. If it's equal to 0, the system's at equilibrium. And if it's greater than 0, then it's not spontaneous as written. And it might move spontaneously in the reverse direction. However, the standard Gibbs free energy does not tell us about whether it's necessarily spontaneous. Its main piece of information is it tells us, are we at what are we like when we're at equilibrium? So if it's less than 0, then the equilibrium favors the products because that means our K is greater than 1. And if it's greater than 0, if delta G naught is greater than 0, then our equilibrium favors our reactants. K is less than 1. So this is very important stuff to know right here. You should know this sheet inside and out and sideways because this is the description of thermodynamics and chemistry right here. So let's do an example, see all this stuff come alive, and we're going to go through it fairly quickly because you can skip through and check these things out. So our question is this. We got reaction A plus B goes to 2C. We're given some standard information about them, and we're asked a few questions. Is it spontaneous under standard conditions? Is it spontaneous when we write it, when we have a certain setup that's not standard, 0.25 molar of my reactants and 1 molar of my product? And what's the equilibrium constant? All of these are the kind of questions you should expect to see on an exam. So let's do the first part. We're given in here our respective Gibbs free energies of formation. Those are our delta G's of F. So we have those available to us so we can use Hess's law to calculate this. Now notice the 2 there, we have to go up to our balanced reaction and we have to indicate and use the 2 from our stoichiometric coefficient right here, and we have to use it within our calculation of Hess's law. If we plug in our values, we get a nice simple thing of minus 5 kilojoules per mole. The question is this reaction spontaneous under standard conditions? You betcha. Minus 5 means if I set it up under standard conditions, this thing would be spontaneously moving towards equilibrium and making more product. So since delta G naught is negative, this reaction will proceed spontaneously in the direction written if we start at standard conditions. But what if we weren't at standard conditions? What if our conditions were slightly different? What if we had 0.25 molar of our reactants and 1 molar of our product instead of having 1 molar of everything? What if that was the case? Well, now we have to go and use our equation that delta G is equal to delta G naught plus RT natural log of Q. If I look at my reaction Q, I can substitute in my actual reaction quotient, which is C squared, the concentration of C squared, divided by the concentration of A and the concentration of B, both raised to the first power. Remember, those powers are the stoichiometric coefficients. All I have to do now is plug in my values. But as I do this, I want to note something. I can cross out my Kelvins right there just fine and dandy, but when I take a look and I'm thinking about adding these two together, I've got kilojoules on one side and joules on the other. So I implore you to use units when you put your numbers down for every calculation at all time. And the reason for this is so that you can see these kind of issues pop up. Well, because there's kilojoules and joules, we have to make those the same. So I have to add a term here that will allow me to cancel out my joules. And now I have kilojoules per mole on both sides. Or not on both sides, but in each term. And now I can do the math. And if I calculate it, I get 2 kilojoules per mole. And lo and behold, this one is not spontaneous in the direction written anymore. Instead, it's going to move left to reach equilibrium. It's going to move towards reactants. So the conditions can change which way we move, just as we saw when we studied equilibrium. Okay, well, the last part is, what is the equilibrium constant? And this is a pretty common question on a test, and there's one pitfall that you've got to overcome. If you remember it, you're going to have no problem. So first and foremost, here's the relationship we found. I want to remind you, it's not going to be given to you. You're going to have to derive this or memorize it. I don't know why you'd ever memorize it when it's so easy to derive. So if I rearrange this, I find that the natural log of K is equal to this negative delta G naught of reaction over RT. I recommend that you do this as I'm showing you because it simplifies the math. You're less likely to make a mistake this way. So what I get here is when I substitute my values in, I get this negative 5 kilojoules per mole, and I put in my 8.314, my 298.15. But now let's look at the units. Take a close look. Once again, I have the improper units. They will not cancel out. I need my joules and my kilojoules to cancel out here. There's my joules. There's my kilojoules. So to do that, I have to add a term. And when I add that term, I can see that my units start to cancel out all over the place. And I get exactly what I should get, which is a dimensionless number, which is 2.017. No units on it. That's because when I raise something to the e, or I take the natural log of it, it can't have any units. So to undo this natural log of k, I have to raise it to the e. So that means I have to raise both sides to the e, or not to the e, I have to take e to the both sides. And when I do that, I find an equilibrium constant of 7.5. So as we see here, the equilibrium constant says that since it's greater than 1, it says that this reaction at equilibrium prefers the products. There we go.